Oh, okay. Let's get this day over with before anything else goes wrong. Okay. Um, all right. So we're going to be focusing on PDEs defined on a bounded interval, like we did before for separation of variables. And you can actually think of what we're going to see here as another perspective for um, on the approach of separation of variables. But we want to cover different kinds of PDEs with different inhomogeneities, like non-homogeneous, PDE itself or non-homogeneous boundary conditions, and try to break these down into simpler problems, and also reduce PDEs to ODEs that may or may not be homogeneous. Okay. Actually, okay, what I'd rather do here, I'm gonna unshare and reshare. So focusing just on the notes. Okay. All right. So even though it's oddly enough, even though it's still a chapter for a wave equation, the approach I'm going to show you here can be applied to either heat or wave. Okay, so finite sine Fourier transform, whether it's sine or cosine. Okay, sorry, I heard some background noise there. Okay, all right, all right. Because when you're using a Fourier transform, we've seen the Fourier transform used on an infinite domain. And when you're using it on a finite domain or bounded domain, bounded interval, they refer to it as a finite Fourier transform. That could be a sine or cosine transform depending on the boundary conditions. So here we have the finite sine transform, which you can also think of as an inner product of a function f of x with these basis functions sine n pi x over L. Now you may recognize these as eigenfunctions of Sturm-Liouville operators that we would encounter when using separation of variables. And back in those early separation of variables problems, what you needed to do was express a function expressed as a series such as this one, and you'd have to find the coefficients. And the coefficients would be found by evaluating these integrals. So we still are the exact same integrals, but now we're referring to it as a finite Fourier transform, in this case, a finite sine transform. So it's the same so operationally, it's the same thing, but from a different perspective. So capital Sn refers to the coefficients of f of x in this sine series, and then so taking this series to reconstruct a function f of x, that's called the inverse sine transform. So finite sine transform gives you the coefficients. Inverse sine transform reconstructs the function of x from those coefficients by taking this linear combination. Okay. So if you have a PDE, a heat or wave equation that has Dirichlet boundary conditions, meaning that the value of a solution is u is specified at the endpoints. So u of 0t equals something, or u of lt equals something, as opposed to the derivative. By contrast, if you have Neumann boundary conditions that specify du dx at x equals 0 or x equals l at the endpoints, use a cosine transform. So very similar, just swapping sine for cosine to get the coefficients of a function f in this Fourier cosine series representation. And once you have the coefficients, and notice they're indexed starting from 0, as opposed to a sine series, they're indexed starting from 1. And you can reconstruct f of x from these coefficients, and that is the typo. That is the inverse cosine transform. Sorry for the copy and paste bug there. So the usefulness of both of these transforms is to reduce a PDE to an ODE to cover the time variable. So what I'll do is show you an example to illustrate the use of these transforms. Okay. All right, so suppose I have function 1 on the interval 0 to 1. So capital L would be 1 in this case. Okay, I'm actually going to move this to a new page. Okay, so now we take the finite sine transform. So my function, I'll just fill it. It's a 1, but I'll fill it in explicitly here just so you can see where it goes. So whatever function f of x you have goes here. And we're integrating from 0 to 1 of sine n pi x, because the length of the interval L is 1 in this case. So we go ahead and evaluate the integral, and then plug in the limits. And what we find is that when n is even, we have cosine of an even multiple of pi, which is always equal to 1. So they cancel out and give you 0. But if n is odd, then we have terms adding together instead of canceling, and we get 4 over n pi. And you may recognize this from some homework problems where these coefficients have popped up. So then, to take the inverse transform, okay. So what would happen is, okay. Here, I want only odd numbers down here. So if I start with n equal 1 to infinity, then this gives me 1 over an odd integer, and then and a 4 over pi I've just factored out. And since this only applies for odd n, then I'll have that same expression in here to cover all sine of an odd integer times pi times x. So then we sum over. So the sum is over all n, but what we get here is always 1 over an odd integer times sine odd integer times pi times x. So for x between 0 and 1, this infinite series will converge to 1. Well, one thing to point out, though, is these sine functions, if you plug in x equals 0 or x equals 1, you're always going to get 0. So you're not going to see that kind of convergence at the endpoints, and the so at any x between 0 and 1, you'll still get convergence to 1 eventually, but at the endpoints, convergence is slow because you have that disconnect. That here we're constructing a function that is going to be 0 at the endpoints, but here this is always equal to 1. Whereas if you have a function that is already equal to 0 at the boundaries, convergence would be much faster. Now, some properties of these transforms that will be useful for solving initial boundary value problems. You have to be able to transform derivatives with respect to x. So these rules will help for both the sine and cosine transform. So if you take the sine or cosine transform of a derivative with respect to t, that's just a derivative of a transform with respect to t, and similarly for a second derivative. So when it comes to derivatives with respect to time, derivative of a transform is the transform of a derivative. Not so with derivative with respect to x. Now, for these kind of PDEs, heat or wave equation, the only derivative with respect to x that we tend to encounter is the second derivative with respect to x. So that's what we give here. So what happens is a transform of a second of uxx is going to be minus n pi over L whole thing squared times the transform of u, but do not forget these terms added on to the end. These are boundary terms. Notice that for sine transform we have u, because this is what is specified on the boundary, so you can incorporate your boundary conditions here and here for x equals L. And then for cosine transform, if you have Neumann boundary conditions, du dx is what's specified on the boundary. So again, your boundary values would be filled in here and here. And the way you establish these rules is when you're using a definition of a finite sine or cosine transform, you fill in uxx in here, use integration by parts twice, and that will result in these rules here. So now I'll show you how you can use one of these transforms to solve an initial boundary value problem. So here's a problem we'll illustrate on. So we have initial boundary value problem for the heat equation. And here we have a PDE that is non-homogeneous. We have this source term here. The boundary conditions are homogeneous. And then here we have our, I'm sorry if I said heat equation. I don't recall if I did. Wave equation, because of the UTT. And here we have two initial data for u of x0 and then the udt of x0. All right. Now, first thing you do, you look at the boundary conditions, and those tell you which transform you should use. And it was caused some difficulty in a homework problem some time back. When u is specified, that's Dirichlet boundary conditions, you must use a sine transform. If it's du dx that is specified, that's Neumann boundary conditions, you should use the cosine transform. So here we have u is equal to 1 as our initial data. So we can use that result to take a Fourier sine transform of the initial data. And then we use the rules for transforming derivatives with respect to t or x to obtain a transform of the PDE. So for our derivatives, okay. This is what we end up getting. Okay. So if actually what I'll do is I need to fill in an intermediate step here. So I have the hold on. Okay. The transform of UTT, that is going to be equal to Sn double prime of t. So the time derivative of the transform. Okay. So by notation, I'm using Sn of t. That is the Fourier sine transform of u. And then we have to handle second derivative with respect to x. So that's going to be equal to, if we consult the rule for that from earlier, we have this, where in this case, L, capital L is equal to 1. So I have this expression here, so minus n pi squared. Okay. So I need to have s. Okay. So what I'll have is minus n pi squared Sn of t. Now, the reason why the transform is a function of t here is because u depends on t. So the finite sine transform takes a function of x and gives you coefficients Sn. But when the function depends on other variables too, those other variables show up here. So the coefficients depend on those variables. So in this case, t. So we have this plus 2 pi, and if we refer back to a rule for uxx for the rest of it, sorry, it should be 2n pi. And then I have this boundary value plus this alternating factor times the other boundary value. So I'll go ahead and fill that in. So 2n pi u0t plus minus 1 n plus 1. I'll show you this in a moment. U of 1t. So that's what we have here. But now we need to consult the boundary conditions for this problem and see what that would give us. Well, the boundary values are both 0. So that part of the boundary terms is going to go away. So we're just going to have minus n pi squared Sn of t. So from our PDE, we have the UTT becomes this, the UXX becomes this, and then we also have our source term, sine pi x. Okay. Yeah, sine pi x. So the transform of that is going to be 2 times the integral from 0 to 1 of that function, sine pi x, times sine n pi x dx. But these functions are orthogonal. So so what that means is okay. This is going to be equal to it's going to be equal to 1 when n is equal to 1 and 0 otherwise. Because if I set n equal to 1 here, this integral will turn out to be 1/2, and then times 2 would give us 1. So when you're in source term or initial data, it's already a linear combination of functions of this form. The coefficients in that linear combination give you these coefficients here, the Sn. So for the source term, we only need to include this when n is equal to 1. Otherwise, we don't include anything. So putting everything you see here together, and recall that PDE is UTT is equal to uxx plus sine pi x. So the transform of UTT gives us this that goes on the left side, and then we have this part from uxx that goes on the right side, and then only for n equals 1, we include this. So from our PDE, taking a transform of that, we get this family of ODEs that we can solve for Sn of t. So for n equals 1, we have this special case that involves the source term. For all other values of n, we have this. So questions about how the ODEs came about from the PDE. All right. Now, okay, so this ODE is non-homogeneous. So there's methods you learn in your first ODE course, like methods of undetermined coefficients or variation of parameters, to solve this. This is a simpler one because it's a homogeneous PDE. In both cases, you would use like methods you learn in class like that, like characteristic equation and the roots of that. But so using those techniques, what you get for a general solution is typo there. Okay. So we have a combination of sine and cosine of pi t, and then for the non-homogeneous part, that adds on this constant c. And then so now we need to look at the initial conditions to determine what these coefficients will be. Whoops, not here. Okay. So S1 of 0 comes from the finite sine transform of u of x0. Well, we have that here. For a case of n equals 1, it would be 4 over pi. So 4 over pi is the initial value for S1. But we also, there's a second order ODE. So we need two initial conditions. S1 prime of 0. For that, we look at our other initial condition for du dt of x0. Well, that's just going to be 0. So we'll go ahead and fill that in. So, so taking those into account, what we find is that there's no sine term. Like if I take a derivative of this, and I get minus a sine pi t plus b cosine pi t all times pi, I plug in t equals 0, then this part's going to be non-zero unless b is 0. So that's why there's no sine term. We only have a cosine term. So if I set t equals 0 in here and the derivative and set them equal to these values and solve for a, b, and c, then this is what I get. Okay. So that's my S1 of t. Now what about n greater than 1? Those are homogeneous ODEs. So those are easier to solve. You just get a constant times cosine n pi t, because So Sn of 0 is equal to n pi for n odd. Sn of 0 equals 0 for n even, and Sn prime of 0 is always 0. So because both initial conditions are 0, then the solution is 0 for all even values of n. For all odd values, we just have the initial value times this cosine. And because of this initial condition being 0, that's why there's no sine term. So now we have Sn of t for all n. Here's for case n equals 1, and then here's the rest. So now I can take the inverse sine transform. So I take S1 of t multiplied by sine pi x. So that term is different from all the rest, so it's written separately. And then for all other odd integers, so n equals 3, 5, 7, etc., I'm going to have, okay, so what I have here is my sine n pi x, where n is odd. And then these values go here with a 4 over pi factored out. And that's the final answer. So questions about how that was solved? So you take the appropriate transform, sine or cosine, depending on boundary conditions, of your PDE and your initial conditions, and that gives you a family of ODEs with initial conditions for them. You solve them using techniques from your introductory ODE class, and then take the appropriate inverse transform, which means multiplying them by the appropriate, their solutions by the appropriate sines or cosines, and then summing an infinite series. But what we often see is that we have special cases, like certain values of n work out differently from others, which makes it a bit more tedious. Now, the next thing we want to talk about is an important concept called superposition, because you could have PDEs or boundary conditions or initial conditions that may or may not be homogeneous. And when these problems are, when the PDE is linear, you can take a given initial boundary value problem and break it down into simpler problems, and then you can just add the solutions together. So then solving each individual problem is less tedious. So your overall amount of work will hopefully be less, or at least you're less mistake prone. Okay. So let's suppose I have this initial boundary value problem. So here I have my initial data, sine 2 pi x. This is a heat equation, and I have a non-homogeneous PDE. I have a source term here. So what I can do is break it down into two problems. So notice the first one, PDE is the same, boundary conditions the same, but my initial data is 0. So then that gives the, if I use, for instance, a finite sine transform to get ODEs, the fact that these ODEs would have 0 for an initial value simplifies the solution formula. If I have the other problem, same PDE except the source term is gone. and then I have the initial data. So then I can solve that by whatever means, like the separation of variables, or I can still use a finite Sine transform, but then my ODEs would be simpler. So then what you can do is you can just solve this, and then add those solutions together, and that will give you this. This is the solution of this one. So that's what superposition means, that you're breaking a initial boundary value problem that has now it must have a linear PDE because you want to have solutions of your two individual PDEs be a solution of an original one. So it gives you a way to break things down into problems that are hopefully less painful. So in this example, this is a solution of the original problem. This term is the solution of the first problem we decomposed into that had the source term but no initial data. Whereas the second term is the solution of this problem that had non-zero initial data but no source term. Okay. Now, here the original problem had homogeneous boundary conditions all the way, but we saw that can be broken down too. That if you have because you find a function that satisfies the boundary conditions, and so then you can subtract that off and deal with homogeneous boundary conditions after that. So if I consider this general initial boundary value problem, so I have a non-homogeneous PDE, and I have a source term, but my initial data happens to be 0. Now here I have Dirichlet boundary conditions. The U is specified. So if I'm going to solve this using a finite Fourier transform, I should use a Sine transform. So let's suppose that I express my source term, f of xt, as a Fourier sine series. Now, because of little f depends on t, my coefficients, capital Fn, those must also depend on t, because the Fourier transform only covers the x dependence. So here is how I would take the finite Fourier sine transform by working out these integrals for whatever little f I have. So here too, I can apply the principle of superposition by decomposing the source term. So let's suppose from this PDE, I solve this PDE, where I have ut equals uxx, but applied to un, not all of u. And then in here, my source term, I have just one of these terms, not the whole thing. Same boundary conditions, same 0 initial condition. So in other words, I've used superposition, but in a different way. I've broken down this one PDE with a source term into a whole one parameter family of ODEs, each one having a portion of little f. So if I were to add all of these PDEs together, I would recover this. But the idea is now I can solve each one of these and similar to the example that I showed you before, where you had a source term that was just plain old sine n pi x, hopefully this one would be simpler than solving this all together. So, because what actually ended up happening is the solution to each one of these problems has this form. It's some function of t times sine n pi x. And actually, the reason why that assumption works is because there's no initial data here to consider. So it's very important that be 0 to make this work. Because what would happen if I take the if I substitute this into the PDE, then I would just get UN prime on the left side. Then I would get this from taking second derivative with respect to x on the right side. And then I would have this term. Because what I do is, this is what I would get after dividing through by sine n pi x. You get a sine n pi x in every term. You cancel it out. And this is what you have. Now, the thing is, when you're taking a finite sine transform of this, for your solution, you do have Fourier sine coefficients for for all indices. It's just that for every index except this n here, you would have no source term in your ODE, and you'd have 0 initial data, so you'd end up getting just 0. So solving this ODE is enough to solve this problem because the solution has this form. It just has one term, not infinitely many terms. And the initial condition comes from the initial condition here, it would just be 0. So now you can solve this non-homogeneous ODE with a 0 initial condition. So then what would happen is, talk a little further here. So u n of t is equal to, so we'd have an integral from 0 to t, and I would have the exponential with the argument t minus s times fn of s ds. So when you have a ODE with a source term like this, that's the solution formula. We've seen this from way back from lesson 9. We were covering non-homogeneous PDEs for the first time. And this is all we have for the solution, because normally there would be another term, but that would involve the initial value, but that's 0 in this case. So then, so then I have un of xt would be equal to this this integral times sine n pi x. And now that you have each one of these, we go back to the original problem of finding u of xt. That'll be the sum of all of these. Okay. All right, so that would be like the final answer. And sure enough, if you plug in t equals 0, you're integrating from 0 to 0. Well, that would be 0, and sure enough, and that's what you want, because the original IBVP had initial data of 0. Okay. Whereas if I take a derivative with respect to t of this, then I would end up with this integrand. So the integral itself would go away. Whereas if I take a second derivative of this whole thing with respect to x, I'm going to get each term here multiplied by minus n pi squared. But also taking a derivative of this with respect to t, well, there's two parts to it because there's a t dependence here and a t dependence here. So if I want to okay. All right, so if I take all of this integral, dang it. Okay. Now before I take a derivative of this, I'm gonna write this a little differently, because anything that doesn't depend on s, I'm allowed to factor out. So I could factor out e to the minus n pi squared t. So then I'll just have that left on the inside, and then I'll just cancel the minuses. Okay. And then to take the derivative of all this with respect to t, I would need the product rule. All right. So then applying the product rule will give me two terms. Dang it. Okay. Sorry, I got a bit of a mess to clean up here. Okay. So for each half of a product rule, for this first half, I'm differentiating only this part. So then I would end up multiplying by minus n pi squared. Okay. And then for this part, I'm leaving the exponential alone. Okay. And then differentiating this, but that's here I'm taking derivative with respect to t of an integral with respect to t over t is a limit, so I'm just going to get the integrand with t plugged in for s. But here I have e to the minus n pi squared t. Here I have e to the plus n pi squared t. Those will cancel. Oh, the ds goes away also. So now I just have this series. But that's just f of x, little f of xt. So really what I get is, okay. Okay. And then for uxx, I take a derivative of this whole thing with respect to x twice. Well, this part doesn't depend on x at all. It's like a constant. I take a second derivative of this, and that's just going to give what I had before, the first half of what I got when differentiating with respect to t. Okay. So here, ut really is equal to uxx, because these parts match, but plus little f of xt. So that confirms that it really does satisfy a PDE. And certainly, so, and I already mentioned how it satisfies initial conditions. For boundary conditions, plug in x equals 0 or 1, all the sine terms will be 0, so it certainly satisfies the boundary conditions. Okay. All right. So questions about what happened here with either usage of superposition. Here I broke up a source term. You can use the same idea to break up, for instance, an initial condition. So you break it down to multiple problems where you're solving the same PDE, same boundary conditions, but individual terms of your initial condition, and then add all those together. We also have time for homework questions if anyone has those.
I do.
Yep.
Our question 19. Those are both the ones where it was the like rough sketch, the solution. And I was wondering if you could kind of walk through how to think about that.
Okay. So the important thing to keep in mind with a wave equation is that there's this notion of propagation, which visually you can think of as a shifting graph. Like with the D'Alembert solution formula, what you have is your initial data. You have half of it propagating to the left, and the other half propagating to the right. And what you see from a solution formula, you'd have like f of x plus ct, f of x minus ct. So it really is a shift of a graph. So you want to have that kind of phenomenon showing up in your sketches of solutions to a wave equation to show that kind of behavior is happening. Like in the first one, at first everything is 0 because that's your initial data, and but then you start to have some non-zero content coming in due to the boundary condition on the right side. It's equal to sine t. So you end up having a non-zero value at the rightmost boundary. So especially when you have a case where a solution is like your initial data or boundary data is mostly 0, but you have something that's non-zero, that's where this kind of propagation is most apparent. So in this case, it's happening at the right edge at x equals 1. What as T increases, whatever's happening at the right boundary should be shifting to the left. And I actually went ahead and wrote some MATLAB code to numerically solve this problem. And what I found interesting was, and the thing is, I would like to show it in class, but people are still working on the problem. So I feel like if I showed the plots of a solution, then you'd know what the solution would look like. But what's interesting is it's reminiscent of ocean waves, because you think of waves heading towards the shore. The left boundary condition is u of 0t is equal to 0. So you can think of that as being like the shoreline. At that point, the height of the water would have to be 0. But at the right edge, where like water's coming in towards the shore, that there's a because you have these rolling waves coming in, the height of the water at the right edge is varying. So for a relatively highly simplified model, it actually does a surprisingly good job of illustrating that kind of behavior. Oddly enough, the second one, 19.2, is that's one that can be solved without too much trouble, just because of the convenient choice of one thing is homogeneous boundary conditions, and also you have this simple form of initial data. It was like I think it was sine pi x over 2 or something like that, so in fact, if you assume a solution is that initial data, sine pi x over 2, times a function of t, you can actually use that to figure out what that function would be and see how it behaves. And I know that's not what the problem is asking for, but it would be a way to get an idea of what it's supposed to look like. But very important to make sure that the boundary conditions are always respected. But I know I'll have to be fairly generous in grading those.
Yeah, I think the harder thing to grasp for me is like the boundary conditions versus the initial conditions, like trying to make them both make sense.
Well, and because your solution is going to start out by having some sort of continuous morphing of your initial condition. It's just that but then once you move on, as t moves forward, you kind of forget about the initial condition otherwise, but the boundary conditions have to be respected in an ongoing fashion after that. And because there's some problems, these two are not among them, but it does happen where the initial boundary conditions are not compatible with one another. Like maybe the initial condition is 0 at the boundary, maybe the boundary conditions are non-zero. So at t equals 0, it's still the initial condition that prevails. But once t gets even a little bit greater than 0, the boundary conditions rule. And that can lead to some odd behavior in the solution when they don't match. But fortunately, in this problem, they do match. So really, the two parts of a problem are governing the solution at different ways. Like so, there's it's a boundary conditions that stick. Okay. I realized I'd got an email question not too long before class, so I took care of that too. But are there any other? Because we still have some time. I want to mention that I've noticed that some among the undergrads have been showing up rather late. I like to some extent wait till everybody's here because no one's having to watch the first few minutes of a video. But if everyone could please, again particularly undergrads, do better uh, to be here on time, that'd be greatly appreciated. Okay. Well, I will end recording at this point, but I'll stick around in case anyone still wants to ask questions.